In this lesson, we will discuss the shear strain and rotation of fluid elements, as well as the vorticity equation. If there is a velocity gradient in a direction other than the direction of motion, shear strain and rotation can occur. That is, if partial u partial y or partial u partial z are non-zero, or partial v partial x or partial v partial z are non-zero, or partial w partial y or partial w partial x are non-zero. Here we have a fluid element at time t with sides dx, dy, and dz. We are looking at the side of the fluid element, so dz is into the screen. We labeled the lower left corner of the fluid element as x0, y0, and the upper right corner as x0 plus dx, y0 plus dy. Let's assume that the fluid element is in a velocity field with velocity gradients in the x and y directions. The x component of the velocity, shown with blue arrows, varies in the y direction. On the bottom side of the fluid element, the x component of the velocity is u at y0. And on the top side of the fluid element, the x component of the velocity is u at y0 plus dy. Since dy is very small, we can use a Taylor series approximation to rewrite the velocity on the top of the fluid element as u at y0 plus partial u partial y times dy. Partial u partial y is evaluated at y0, but we will omit y0 to avoid cluttering the screen. Notice that the difference in velocity between the top and bottom sides of the fluid element is given by partial u partial y times dy. The y component of the velocity, shown with purple arrows, varies in the x direction. On the left side of the fluid element, the y component of the velocity is v at x0, and on the right side of the fluid element, the y component of the velocity is v at x0 plus dx. Since dx is very small, we can use a Taylor series approximation to rewrite the velocity on the right side of the fluid element as v at x0 plus partial v partial x times dx. Partial v partial x is evaluated at x0, but we will omit the x0 to avoid cluttering the screen. Notice that the difference in velocity between the right and left sides of the fluid element is given by partial v partial x times dx. After a time dt is passed, the velocity gradients will cause the fluid element to deform and possibly rotate. It should be noted that the amount of translation, deformation, and rotation that occurs during time dt have been highly exaggerated on this diagram for clarity. In reality, the fluid element will appear to change almost imperceptibly during the small time dt. In order to more easily analyze the deformation and rotation of the fluid element during time dt, we will travel along with the fluid element and superimpose changes that occur. We label the lower left corner as point O, the lower right corner as point A, and the upper left corner as point B. The bottom side of the fluid element, OA, rotates a very small angle, d alpha, due to the gradient of the y component of the velocity in the x direction. Similarly, the left side of the fluid element, OB, rotates a small angle d beta due to the gradient in the x component of the velocity in the y direction. The distance traveled by point A relative to point O is the difference in velocity between the right side and left side, partial v partial x dx, multiplied by the time dt. The distance moved by point B relative to point O is the difference in velocity between the top side and bottom side, partial u partial y dy, multiplied by the time dt. We will use the symbol lowercase omega to denote angular velocity and define the counterclockwise direction as positive. The angular velocity of side OA is equal to the time rate of change of angle d alpha. Since dt is a very small amount of time, the angle d alpha will be small as well. For very small angles, the tangent of the angle is approximately equal to the angle itself. The tangent of d alpha is equal to the length on the opposite side, partial v partial x dx dt, divided by the length of the adjacent side, dx. The dx's cancel out, and we are left with partial v partial x dt. Plugging this expression for d alpha into the equation for omega OA, and canceling the dt's, we obtain that the angular velocity of side OA is the velocity gradient partial v partial x. Now we examine the angular velocity of side OB, which is the negative time rate of change of angle d beta. We require a negative sign because the side OB is rotating in the clockwise direction, which is the negative direction for the angular velocity. Since d beta is very small, it is approximately equal to the tangent of d beta. The tangent of d beta is equal to the length of the opposite side, partial u partial y dy dt, divided by the length of the adjacent side, dy. After canceling the dy's, we obtain partial u partial y dt. Plugging in this expression for d beta into the equation for omega OB, and canceling the dt's, we obtain that omega OB is equal to negative partial u partial y. We can calculate the average angular velocity of the fluid element about the z-axis, called omega z, by taking the average of omega OA and omega OB. Plugging in the expressions for omega OA and omega OB, we obtain 1/2 times the quantity partial v partial x minus partial u partial y. So far we have only examined one plane of motion. Velocity gradients can occur for the z component of the velocity in the x and y directions as well. Additionally, the x and y components of the velocity can vary in the z direction. If we examine the angular velocity about the x-axis and y-axis as well, we would obtain similar expressions. The average rotation rate about the x-axis, omega x, is 1/2 times the quantity partial w partial y minus partial v partial z. The average rotation rate about the y-axis, omega y, is 1/2 times the quantity partial u partial z minus partial w partial x. Using the three expressions for angular velocity about the x, y, and z axes, we can construct an angular velocity vector omega, which is equal to omega x I hat plus omega y j hat plus omega z k hat. Let's plug in the expressions for the three components. Recalling the definition of the curl of a vector, you can show that the angular velocity vector is simply 1/2 the curl of the velocity field. This means the curl operator picks out the portion of the velocity field that causes rotation. In fluid mechanics, it is customary to work with the vorticity instead of the angular velocity. The vorticity is denoted by zeta and is 2 times the angular velocity vector, or the curl of the velocity field. It should be noted that some fluid mechanics textbooks prefer to use lowercase omega for the vorticity instead of the angular velocity. A special case occurs when the vorticity is equal to 0. We call this type of flow irrotational. Expanding the vorticity vector, a flow can be irrotational if all three components of this vector are 0. This means partial w partial y equals partial v partial z, partial u partial z equals partial w partial x, and partial v partial x equals partial u partial y. All three equations must be satisfied for a flow to be considered irrotational. Notice that velocity gradients can still be present in an irrotational flow, so fluid elements can still deform in such a flow. One reason why irrotational flows are of interest in fluid mechanics is because if a flow is irrotational and frictionless, which is also called inviscid, it is possible to use potential flow theory to predict the velocity field. A couple examples where flows can be approximated as irrotational and inviscid are the central core of a flow in the entrance region of a pipe, and in the area surrounding the boundary layer and wake region of an object that is immersed in a fluid, such as a ball traveling through air. The flow inside the boundary layer in both situations is not irrotational or inviscid, and potential flow theory cannot be used to predict the velocity field in those regions. The velocity gradients in a flow can be related to the rate of shear strain of fluid elements. We define the two-dimensional shear strain as the average change of the angle between two lines which are initially perpendicular, such as lines OA and OB. This means the shear strain during time dt is 1/2 times the quantity d alpha plus d beta. The time rate of change of the shear strain is called the shear strain rate, and is denoted by the symbol epsilon with subscripts related to the plane of motion. In this case, we are examining the xy plane, so the shear strain rate is epsilon xy. Earlier we found that d alpha dt is equal to partial v partial x, and d beta dt is equal to partial u partial y. So the shear strain rate can be written as 1/2 times the quantity partial v partial x plus partial u partial y. If we analyze the shear strain rates in the yz and xz planes, we would find similar expressions but with different derivatives. The shear strain rate in the yz plane, labeled epsilon yz, is equal to 1/2 times the quantity partial w partial y plus partial v partial z. The shear strain rate in the xz plane, labeled epsilon xz, is equal to 1/2 times the quantity partial u partial z plus partial w partial x. If the shear strain rate is equal to 0 in all three planes, we have a special case of solid body rotation. Examining the equation for the shear strain rate in the xy plane, solid body rotation corresponds to a case in which partial u partial y equals negative partial v partial x. This means the magnitude of the velocity gradients are the same, but one velocity gradient is oriented in the positive direction, while the other velocity gradient is oriented in the negative direction. For example, here we have a fluid element with the x component of the velocity increasing in the positive y direction. The y component of the velocity changes by the same amount in the x direction, but is pointed in the negative direction. If these are the only velocity gradients present, this fluid element would undergo rotation but not distortion. In general, for the entire fluid element to undergo only solid body rotation, the shear strain rates in the yz and xz planes also must be equal to 0. This means that partial v partial z equals negative partial w partial y, and partial w partial x equals negative partial u partial z.